Imagine this. Out there in the vastness of space, a star just gets a bit too close to this invisible cosmic monster. And suddenly it starts to stretch, pulled apart by, well, incredible forces until it just shreds, rips into this stream of gas and debris spiraling down. It's incredibly violent. We call it a tidal disruption event, a TDE. And today, you're with us for a deep dive into some really groundbreaking new stuff about these TDEs, things we're seeing now thanks to the James Webb Space Telescope, JWST. Our mission really is to unpack how these new findings are changing what we thought we knew about black holes, especially the quiet ones, the slumbering giants. Okay, so let's unpack that term first. Tidal disruption event. What is that basically? We're talking about a huge black hole at the center of a galaxy.
Exactly, a supermassive black hole. And it encounters a nearby star. The black hole's gravity is so strong that the tidal forces, the difference in gravitational pull across the star, literally tear it apart.
Wow, just shreds it.
Shreds it. And that process releases just a massive burst of energy. But the interesting thing is, these events seem pretty rare, or maybe we just haven't been good at spotting them. Since the 1990s, we've only really documented about 100 or so.
100? That doesn't sound like many, cosmically speaking.
Not at all. And it's important to, separate these from active galaxies. Active galaxies have black holes that are constantly feeding, like always on.
Right, the really bright ones.
Yeah. TDEs involve black holes that are usually dormant, quiet. They only wake up, essentially, for this one meal. One unlucky star wanders too close, and bam.
Okay, so that begs the question. If they're so dramatic, these huge bursts of energy, why could we seen so few? Why have they been hiding? You'd think something that violent would, shine brightly.
Well, that's been the tricky part. Most of the TDEs we did see before were in galaxies that didn't have much dust around them.
Okay, clearer environments.
Exactly. So the light, like X-rays or optical light from the event, could travel straight to our telescopes. But earlier work, actually by the same MIT team involved here, showed something important. They found that if the galaxy is dusty, that dust can totally block the X-ray and optical light.
Ah, like cosmic fog.
Pretty much, yeah. Makes it incredibly hard to see the initial flash, but, and this is the key insight, that huge burst of light, even if blocked, it heats up the dust.
Okay, so the energy still interacts with the surroundings.
Right, and hot dust, well, it glows, but it glows in infrared light.
Infrared, not optical, not X-ray.
Correct. So this suggested that maybe, just maybe, there were tons more TDEs happening out there, hidden behind these dusty curtains, invisible to our traditional telescopes.
Leaving behind this heat signature we just couldn't detect properly before.
Exactly. We were missing the infrared clues.
And that is where the James Webb Space Telescope comes in, right? It's the most powerful infrared detector we have, built for exactly this kind of work.
Precisely. It's a game changer for this field. So this new study, it was just published July 24th in Astrophysical Journal Letters, and it details how astronomers from MIT, Columbia, and elsewhere used JWST. They specifically targeted these dusty nearby galaxies to look for the aftermath of these star-eating black holes.
And they found them.
They did. This is actually the first time JWST has detected multiple TDEs hidden by dust. It's a big milestone.
I saw a quote from Megan Masterson, the lead author. She had this great analogy. She said something like, with NEOWISE, which is another infrared telescope, right?
Yeah, survey telescope, less sensitive, broader view.
Right. She said, with NEOWISE, it's as if our eyes could only see red light or blue light, whereas with JWST, we're seeing the full rainbow.
That's a perfect way to put it. JWST gives us that full spectrum, the detailed view in infrared we needed.
So, okay, JWST sees in infrared. It sees the full rainbow. But how did they know for sure it was a TDE? What was the smoking gun, the definitive proof?
They were looking for really specific fingerprints in that infrared light, specifically a peak in the light at a very particular wavelength. This peak is created only when material, the stellar debris, is actively falling into the black hole. That's accretion.
Black hole accretion, okay.
Yeah, and this process is so energetic, it produces intense radiation. This radiation excites atoms in the surrounding gas, like neon atoms. It kicks electrons out, they recombine and release infrared light at this very specific, very characteristic wavelength.
And only accretion does that with that kind of energy.
Exactly. JWST is incredibly sensitive to that exact wavelength. And Masterson really emphasized this point. She said, there's nothing else in the universe that can excite this gas to these energies except for black hole accretion.
Wow. So it's basically an unmistakable signal, like a cosmic barcode for black hole eating now.
Pretty much, yeah. It's as definitive as it gets in this line of work.
That's incredible detection capability.
Right.
So they pointed JWST at 4 specific candidates, right? Ones they thought were likely TDEs based on earlier NEOWISE data.
Correct. 4 prime candidates identified by NEOWISE's broader infrared surveys.
And what did they find in those 4?
Yeah.
Were they all the same?
They were actually quite diverse, which is also interesting. One of them turned out to be the closest TDE we've ever detected. It's in a galaxy only about 130 million light years away.
Relatively close, cosmically speaking.
Yeah, practically next door. Another one also showed a burst of X-rays, which sort of adds another layer of evidence.
Okay.
A third one had signs that the gas might be swirling around the black hole at, like, incredibly high speeds. Gives us clues about the dynamics.
Interesting.
And the fourth one was maybe the most intriguing initially. It also had an optical flash detected earlier, and some scientists had actually thought it might be a supernova, an exploding star.
Ah, so potential misidentification.
Right. But JWST looked closer, and the result, those telltale spectral lines, the fingerprints of accretion, they showed up loud and clear in all 4 sources.
All 4. No ambiguity.
Oh, no ambiguity. It definitively confirmed black hole accretion was happening in each case. Masterson put it well again. She said, these 4 signals were as close as we could get to a sure thing. But the JWST data helped us say definitively these are bona fide TDEs.
Bona fide TDEs. Confirmed. That's huge.
Yeah.
So, okay, we know they're TDEs now,
Hmm.
but what does this tell us about the black holes themselves? You mentioned the dormant versus active distinction. Did these findings shed light on that?
Absolutely. This was a really crucial part of the study. The team needed to figure out, was this accretion just a temporary thing from the TDE, meaning the black hole is usually quiet, or were these actually just normal active black holes that happen to be surrounded by dust?
Right. How do you tell the difference?
They used JWST again, but this time looking for another infrared signal, one that indicates silicates, basically, dust. By mapping where the dust was and how it was structured, they got their answer.
And what did the dust maps show?
They found that the dust patterns around these TDEs were really different from what we typically see around constantly active black holes. Active galactic nuclei, or AGN, often have this sort of clumpy, donut-shaped torus of dust around them.
Okay.
These TDE environments didn't look like that. The dust distribution was different, suggesting that these black holes are not normally active. They are, in fact, dormant. The accretion disk, the swirling debris, it must have formed solely because of the recent tidal disruption event. It's temporary.
Wow. So JWST isn't just finding the TDEs, it's characterizing the black hole's typical state.
Exactly. Masterson summarized it. We've learned these are indeed powered by black hole accretion, and they don't look like environments around normal active black holes. And she added, the fact that we're now able to study what that dormant black hole environment actually looks like is an exciting aspect.
That really is exciting. We're getting a glimpse into the lives of quiet giants only when they briefly wake up. So, stepping back a bit, what are the bigger picture implications here for understanding black holes, the universe?
Well, first, it just underlines how powerful JWST is for this specific kind of science.
Yeah.
It's opened up a whole population of TDEs that were effectively invisible before.
A hidden population revealed.
Yes. And the more of these we can find and study, the better. Because TDEs can become really effective probes of the black holes themselves.
How so? What can they tell us?
Think about the details. How much of the star gets ripped apart? How quickly does that debris spiral in and get consumed? Those details, the light curve, the spectral features over time, they can potentially tell us fundamental things about the black hole.
Like its mass.
Its mass, yes, and maybe even how fast it's spinning. These are key properties that are otherwise very hard to measure, especially for dormant black holes.
So each TDE becomes like a little experiment illuminating its central black hole.
That's a good way to put it. And as Masterson pointed out, this whole process isn't instant. She said, the actual process of a black hole gobbling down all that stellar material takes a long time. And hopefully we can start to probe how long that process takes and what that environment looks like. And she added, no one knows because we just started discovering and studying these events. There's so much still to learn.
Okay, so let's wrap up this deep dive. The big takeaway seems to be that JWST has given us these incredible new infrared eyes. We can now pierce through the cosmic dust and witness these incredibly violent, previously hidden events, tidal disruption
It's
events.
definitely.
And in doing so, we're not just confirming the TDEs, but we're actually learning about the nature of the black holes involved, finding out that many are typically dormant, just having these brief, spectacular moments of activity.
That's right. It's really just the beginning, you know? We're starting to understand the diversity of these elements in the environments around black holes much better. The universe keeps showing us it's more complex and, frankly, more interesting than we imagined.
Absolutely. And it really makes you think, doesn't it, as we build these amazing new tools like JWST, how many other incredible cosmic dramas are playing out right now, hidden from view? What else is waiting in that cosmic dust, just waiting for the right kind of eyes to finally see it?